In this lecture, we're going to go through a numerical approach, a numerical example of calculating the change in energy of a rotating system. And when we talk about a rotating system, we also have to take into consideration the energy change that involves any linear movement in addition to the angular movement. So when we talk about rotational motion, once again, rotational motion is influenced and compelled by an external moment of force, which is going to be determined by the application of some external force, provided that that force has a physical separation at a right angle from the point of rotation, which is its moment arm. And so when we talk about a perpendicular distance here, that's referring to the moment arm over which that applied force is acting. So here we see an example of a simple rotating object about its center of mass. We have a force applied to the distal part of this object. Now this force, for convenience purposes, happens to be applied at a right angle, and that applied force is going to induce a rotation from this first position to the second position, and in doing so, the object will experience a change in angle, or just a change in theta. But with respect to the distal part that we're focused on, that distal part will also experience a curvilinear change in position, which will carry linear units to it. And we're going to use the symbol D to represent that curvilinear distance over which that distal part of the segment has moved. And so if we start with our basic definition for work, we know that work is the application of a force times the distance over which that object actually moves. And specific to our example here, we're going to focus squarely on the distal part of the rotating segment and expressing the distance with respect to the length from the point of rotation of the segment, and the change in angle. It's going to be equal to theta times r. Now if we expand this equation, our work equation, specific to D, and substitute the right hand side of the equation, we have force times theta times r, or we can express it with respect to grouping the force and the distance from the axis of rotation to the point of force application. And once again here, our force is being applied at a right angle to the segment. We find that a force times that distance, which is essentially the moment arm for that force, it's going to be equal to the moment of force times the change in angle. Once again here, our change in angle must be expressed in radian units rather than degree units, so we have to do the conversion. Now in terms of translational kinetic energy, we've seen this equation where the translational kinetic energy, or the linear kinetic energy, is going to be equal to 1/2 of the mass of the object that is in motion times the velocity of that object squared. So once again here, we see that velocity plays a considerably larger role than the mass in terms of determining its energy of motion, or its translational kinetic energy. Likewise, the object that is rotating will also have an energy related to its motion, and that's going to be equal to 1/2 times the angular counterparts that we observed in the linear or the translational sense. So recall that mass represents the inertia term an object has in the linear case, but in the rotational case, the rotational inertia is defined by uppercase I, which is the moment of inertia. So in this example, we're going to use the moment of inertia of a rotating object, assuming that object is rotating about its center of mass, times the angular counterpart to velocity, which is angular velocity. And just as a reminder, when we talk about our angular velocity, those must be expressed in radians per second. Now, if we take our attempt to calculate the amount of work performed on an object that is rotating, we're essentially calculating the change in the rotational kinetic energy. And that's going, when we talk about a change, we're talking about the rotational kinetic energy at some final point, subtract the rotational kinetic energy at some initial point. And we're going to take the difference between those in our numerical example. So when we talk about work, work can also be expressed as a change in mechanical energy. But when we talk about rotating objects that may also be experiencing general motion, so in addition to the rotation, an object could be experiencing some form of linear motion as well, we have to consider all the energy terms that we've addressed so far. And that includes any change in the potential energy. So if an object has gained or lost height with respect to a reference, usually the ground, that's going to be added to the calculation of the total kinetic energy, or rather the translational kinetic energy, plus the change in rotational kinetic energy. And so we would group these three terms at the beginning, which is the energy, the total energy at the initial point, and the total energy at the final point. And re-expressing this equation, expanding it to the definition of each of these three variables, we have mgh, which is our equation for potential energy of an object in its final position. That's going to be added to 1/2 times the mass times mass of the object times its linear velocity squared in its final state, plus 1/2 of the moment of inertia times the angular velocity in its final state squared. So all these terms are algebraically added, although the variables are different in each of these three equations. They will yield the same units of energy, which is joules. And that's going to be, and we subtract the quantity, the algebraic summation of the three similar energy terms computed at the initial state of the object. And so we're going to work through an example here of a gymnast performing a backflip. And so in this situation, the gymnast is in the air for half a second, and she reaches this particular position in the middle of her backflip. And so what we want to do is how much work was performed in order for the gymnast to change her position from a standing position to the midpoint of the backflip, and how much power was needed to perform this task. And so we obtain some data that's been provided. So we know the mass of the gymnast is 60 kilograms, the standing center of mass, because we're not going to differentiate the upper leg, the lower leg, the foot, or any of the segments, but we're going to group and model the gymnast as a single rotating segment. And recall very early on when we talked about simplifying our model, although the single rigid segment may not be exactly representative of a gymnast who has segments that are changing angle, it gives us a foundation so that we can work complexities back into the model. So the calculated moment of inertia for the gymnast was provided to us at 9.55 kilogram meters squared. The velocity, the linear velocity of the gymnast is experiencing at this point was captured to be 4 meters per second and rotating at 6 radians per second. And the final position for the center of mass is 2.2 meters. This is a little bit high here, but let's just assume our gymnast launched herself off some elastic surface. Okay, so in the standing position, we estimate the center of mass based upon the data that were provided, and that was taken to be 1 meter. Okay. Now we know in the standing position, angular velocity is going to be 0. The linear velocity is going to be 0, but we know the mass is 60 kilograms. And so what we have on the right-hand side is the final position in question. And so here we've captured an image of the gymnast mid-rotation. And so these data are provided to us. The gymnast is experiencing a linear velocity of 4 meters per second. This arrow is not a vector. This arrow is just pointing to the fact that this value here is applied to this point. So we are only going to consider vertical motion here. So the gymnast has a vertical velocity of 4 meters per second. The center of mass, the moment of inertia about the center of mass was provided to us at 9.55 kilogram meters squared. And the angular velocity, once again, is provided at 6 radians per second with a final position of 2.2 meters. So once again here, as we begin our process, the initial energy of the gymnast taken at this point is going to be equal to the sum of the potential energy, translational or the linear kinetic energy, and the rotational kinetic energy. And so by substituting the values that have been provided to us, we have a mass of 60 kilograms. We input 9.81 meters per second squared for G, and the height was taken to be 1 meter. Now, in a standing position with omega and v equals 0, when we expand and when we substitute into these equations, we see that velocity is 0, angular velocity is 0, both the second and the third term in our summation both go to 0, so we're left with an initial energy that is the potential energy of 589 joules. So moving to the final state that we observed earlier, here we see a final position of 2.2 meters. The gymnast is in motion with a linear vertical velocity of 4 meters per second, angular velocity of 6 radians per second, and the same moment of inertia. So we run the same equations, so we input the potential energy in the final position, the linear kinetic energy, and the rotational kinetic energy in the final positions. We collect our data that have been provided to us, and we substitute those data. So what we're seeing is very similar values here for the mass, or rather the same value for the mass, same value for G, but now we have a new value for height because the gymnast has achieved a new position with respect to our reference, which is the ground at 2.2 meters. But now we have a linear velocity term, a vertical velocity of 4 meters per second. We have an angular velocity at 6 radians per second. Okay, and we have the moment of inertia at 9.55. So working through our terms and summing up the three energy values, we have a final energy of 1,947 joules. And this is not this is just the final energy state, but in order to capture the work done, we have to take into consideration the initial energy state of the gymnast. And so by taking the difference, we just simply substitute the final energy value. We subtract the initial energy value from the final energy value to get a complete value for the work done, which is 1,358 joules. Now, the question also provided some additional data and asked us to compute power. And so we know that power is equal to the work performed over time, and so we take our change in energy divided by time, and 2,716 watts of energy was generated in order to perform that backflip, one other point to make here is that the power is an average power, and because the interval of time is actually quite long here. So although 0.5 seconds doesn't seem like a very long time, in terms of performing these calculations, it's still considered a rather lengthy interval, and so we would just simply say that this is the average power, because moving from the standing position to a position that the gymnast has rotational velocity and linear velocity, the gymnast moves through a range of velocity values that would affect the power generation. So in terms of estimating the power as a result of some force, just to review here, we have work divided by time, which is force times the change in distance. That's the distance over which an object has moved, and that divided by time, isolating the delta D divided by delta t here. So combining these two units will give us velocity. Therefore, the power generated from the application of a force can also be expressed as a force times velocity. In terms of estimating the power as a function of a moment of force, once again here we start with the work divided by time. And work is expressed as the moment of force because we're talking about angular power times the change in theta. There must be some change in the angular position in radians divided by time, and that will give us the moment times the angular velocity. Ideally, if we can calculate those instantaneously, that would be ideal, because that would allow us to track the changes in power generated during an angular movement as a function of time. But if we take those measures, whether it's a linear measure of power or an angular measure of power over wide time intervals, we'll be calculating an average. And so we can calculate average values for linear or angular estimates of power, or we can calculate instantaneous measures if we take time intervals that are sufficiently small. And so just to finalize our units for angular power, it's going to be equal to Newton meters, which is the unit for the moment of force, times the angular velocity expressed in radians per second. And recall that 1 Newton meter is equal to a joule per second, which equals watts. So this will end this part of our lecture, and our next part we will work through another example of a rotating segment.